So we had some confusion regarding the Mohr-Coulomb failure model and the Mohr circle. All right. So today the class, what we are going to do is we are going to, as far as possible, reduce those doubts and address those doubts so that we can understand what is actually the Mohr circle means and what is the Mohr-Coulomb failure model. Okay, so we are going to discuss the Mohr circle and the Mohr-Coulomb failure model. Of course, the basic introduction of the Mohr-Coulomb failure model and the Mohr circle. So we have been discussing a lot many times that we express the shear strength of soil using this equation. So the shear strength of soil, tau, we express it with cohesion plus the frictional resistance. So here tau is the shear resistance of the soil and sigma is the normal stress on the failure plane where it will shear off, where the sample will shear off. So now we are going to address the two things. So in the Mohr-Coulomb model, we have this failure surface. So this is the failure surface. So we will see how we obtain this. All right. And we have the Mohr circle. Now this is the Mohr circle. So this is the Mohr circle at failure condition. So what do we mean at failure condition? We will see as we proceed. But first of all, we have to understand that Mohr circle, it is basically the representation of the stress state within the element. Of course, we will, as we go on, we will see. But we should not compare we should not put together the two elements. So this is a separate element and this is a separate element. Together, they form the Mohr-Coulomb model. All right. So this is basically the Coulomb friction. So Coulomb friction, we will see what is Coulomb friction, and this is the Mohr circle. So Mohr and Coulomb model. Okay. So we have been seeing that that we do 2-3 types of tests. So here S is the radius of the Mohr circle, and T is basically the center of or sigma m, that is the mean, not T, sigma m, that is the mean, is the center of this Mohr circle. All right, and we define the Mohr-Coulomb failure surface in this manner. All right, we draw a tangent to these circles and we get the Mohr's failure surface. Of course, we have been discussing that, but we are going to see some basic aspects we are going to see. So before going to that, we have to first understand. So as I have told here, so the Mohr-Coulomb model has two aspects. One is the Coulomb friction and one is the Mohr circle. So first let us concentrate on the Coulomb friction. All right. So how it is, how it evolved, how it got evolved. So we have to look back into our basic science topic. So that is the Coulomb friction. So what is friction? So we have an object placed on another object. And this object, as it is shown here, it has a weight W. So that means it is exerting a force onto this object. So this object, the top object here, this object is applying a force onto this object. That is its own weight. Okay. And similarly, this bottom object, this bottom object exerts a normal force, this normal force, onto the object at top, right? So when we start, suppose we start pulling this object in this direction. So we are pulling this object. So we are increasing the force. So we applied 1 Newton force, 2 Newton force, 3 Newton force. All right. So we are increasing the intensity of the or the magnitude of the force. We are applying more force. We are increasing the force here. All right. So in this manner. So ultimately, what will happen at a particular value of force, at a particular magnitude of force, this material or this object, it will start moving. As soon as it moves, the force required to keep it at constant motion will reduce. So we have learned that this extreme value, this extreme value of this force which is required to just make it move is the static friction. And the force required to keep it at constant motion is the kinematic friction. Or kinetic friction. All right, so kinetic friction. So if the weight is reduced, if the weight of the material is reduced, so definitely this is the weight here. This is the no, this is the weight here. All right, so this is the weight, and this is the frictional force. So if the weight is reduced, so suppose the weight is reduced up to this point, so the force required to make it move, it will be this much. So the object will then start moving at this point, and the kinetic friction will be of this manner. If we reduce the weight further, if here, so the force required to make it move will be this much. All right. So one thing you note that weight, whatever weight it is having, it is similar to the normal force. It is equal to the normal force. Now alternatively, what we can do is, so we have, suppose we have a weight W. So initially we have a weight W. Sorry, here. So we have a weight W. So this is the normal force. If we divide it by the area, it will be normal stress. So we have the normal force. And then we go on applying the tangential force. If we divide the tangential force by the area of contact, it will be the shear stress. So when we go on applying the force, so force is increasing. At a particular point, it will move. So it will start moving. So this is the kinematic friction and this is the static friction here. Now if I apply additional force here, so F suppose 1 or suppose N1, okay, so N1 I am applying, so the normal force is now N plus N1, so this is N plus N1 here, so this is N plus, so this was W equal to N, now this is equal to N plus N1. So now if I apply the force, start applying the force, it will not move, and we will go on increasing the force. Ultimately at a point, it will start moving. So this is the force required to make it move. corresponding to this normal force. And this is the point of static friction. All right, maximum value of static friction. So again, after moving, it will reduce in this manner. So similarly, if we again increase, suppose now n1 again plus n2, so we have this point, so n plus n1 plus n2. So it is like W. So here Mohammad Hussein was standing only. All right, so we have W. Then n1 means on top of Mohammad Hussein I am standing. So the weight increased. Then on top of me, suppose Swagata is standing. Okay, so now n plus n1 plus n2. So now again, all of you are pulling, all the rest of you are pulling, pulling, pulling. It is not moving, and you are going on increasing the force. You are, giving the more effort, and ultimately at a particular value, it will again move. Right. So this slope, is mu equal to tan of phi. All right. So phi is equal to tan inverse of mu. So this particular experiment can be replicated as this. So here, if we go on increasing this angle, then at a particular angle, this mass will slide over this board. All right. So this mass and this board has a friction. So that is the mu s. So the angle at which it will start sliding, that angle theta is equal to the angle of internal friction phi, almost approximately equal. All right. Some differences may be there, almost approximately equal. So soil is also a frictional material. All right. So the shear resistance of soil is derived from interparticle friction. Okay, so we can consider this as one particle of soil, and there is one particle of soil, and there will be other particle, and there will be friction among all these particles. So the shear resistance of soil is basically developed from this friction. So as of this, as considering this, so if we zoom into this contact surfaces, then we will see that there are points of contacts and there are contact stresses there. All right, so like that. So soil also, here, if we consider the direct shear test, so a direct replication of this concept is the direct shear test. Okay, so here what we can consider is, we can consider this mass of soil to be divided into two mass. All right, so this is the failure plane or the slip plane. All right, or the plane of shearing, whatever you say. All right, so this is the plane. So this mass will move or shear in this direction, and this will shear in this direction, or it will remain constant, as we can say. So this mass will remain here itself. This mass will remain here itself, just like this one, and this mass will move in this direction. So just like what we have discussed in the previous slide, all right, so with increasing normal force, the force required to shear is also increasing. Here also, with increasing normal force, the force required to shear will go on with increasing normal force. So this is the normal force. So normal force is increasing. With increasing normal force, the force required to shear will also be go on increasing. So this is N1 corresponding to F1. All right, and this is N2 and this is F2 and this is F3. Now mind you, if it is failed, so it will drop, and this is the kinematic or kinetic friction here. Right, just like soil. Soil also will feel like this and it will show a behavior like this. All right, it will feel like this and it will show a behavior like this. So in case of soil also, we will have similar curves. Okay, so the friction, this is the static friction here in this case. So similarly, that is the maximum peak friction that it is developed here in this case of soil. Similarly for N2, this is the case, all right, and it is failed, and this is N3, so it F3, we have to apply, increase the force up to F3, and then it will fail, all right. So these are the points where the soil started shearing, all right, or it started shearing. I mean, the elastic range has crossed over, all right. So the elastic range has crossed over. So same concept applied here. So that is what soil is, a friction, I mean frictional material. So the interparticle friction is what gives rise to the shear resistance of the soil. So it is dependent on the normal force. So it is dependent on the normal force. All right. So the shear resistance of the soil is dependent on the normal force. So alternatively, that also, if we consider, if we place this mass on top of here, and if we increase, so at a particular angle, it will slide down. So that is the, in this case, so when we obtain the mu is equal to tan phi, so in this case, the angle phi is called the angle of internal friction. Why internal friction? Because it is happening within the soil mass. All right, particle to particle of the soil mass. So that is why internal friction. All right, so angle of internal friction. Now this angle theta, when it will start moving, is called the angle of repose. All right, and they are of the same value. All right, same value, and that we observe when we pour sand or granular soil into a flat surface. So suppose there is a flat surface. So we pour the sand, all right, and it will arrange itself into a mound of this kind, into a mound of this kind. And that angle of the mound will depend on the interparticle friction of the material. So here you see fine sand. So here you see fine sand here. So the angle of repose is less. As we go on coarser material, so this is coarser material. So this is very fine rounded particles like this. And this is bigger, coarser material. All right. So coarser material. So more friction, interparticle friction, and therefore a higher angle of repose. And as we go on, so these are angular pebbles. All right. So like stones, small pebbles. All right. So here you see it is significantly high. So here what is happening is interparticle friction is playing. All right. So what happened here on this surface? So same thing is happening at this points of contact of the soil particle. All right. So that is the angle of friction. So that is how. So that is how this. So there are the forces onto the soil. All right, and these are the forces, and that is how this mound is being keeping stable. All right. So these are the interparticle normal forces. All right, and there will be the shear forces. All right, there will be the shear forces just like this. So this angle of repose is also almost comparatively equal to the angle of internal friction. Okay, so you can correlate this to this. So here there is one solid particle, there is one solid particle, so there is one solid particle, all right. So we have, so here is one solid particle, so we have the points of contacts, all right, just like in the previous case here. So as we have discussed, so we have this soil mass and we have this mass on top. So we have this mass on top and we have this bottom object, we have this bottom mass, all right. And as we increase the normal forces, so suppose we give one N1 and we will require F1. So first we plot N1 and then we plot F1, all right. And how we will get F1? So we will plot the normal displacement, I mean the displacement in this direction to the force, all right. So this is the displacement and this is the force. So it will increase, increase, increase. The force will increase up to F1. Up to F1 it will increase, and then from F1 it will slide down, all right. So that is one. So this is F1. Then we increase to N2. So this is N2, all right. So as we increase to N2, so now again we apply the force, so it will increase, increase, increase up to F2. So F2 will be required. So here if we plot it, so we will see that it is increasing, 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 and at F2 it will fail. So that is F2. So that is F2. And ultimately, joining all these points, we get the angle of internal friction of the soil. So that is what Coulomb did. Okay, so Coulomb obtained this failure surface. All right, so he obtained the function of normal stress to the tangential stress. So if I divide it by the area, so this is the normal force and this is the tangential force. If I divide it by the area of contact, if I divide it by the area of contact, I will have the normal stress and I will have the shear stress. So Coulomb obtained this, right? Now, so this is the direct shear. So now in the triaxial, what we do, so when we consider a soil element in situ, so the soil element is at a depth, so stresses are acting from all directions. So stresses are acting from all directions. So to find out the behavior of the soil to various stress state condition, all right, stress state. So kindly remember this term because we will again use that when we will see the Mohr circle. Okay. So when we say stress state, so we have to replicate that. So to do that, we do the triaxial. So we have already discussed that in the triaxial, we apply the cell pressure using the pore fluid, all right, and the cell pressure is applied at each and every point of the soil. So here also sigma 3 is applied, cell pressure is applied. So this is cell pressure at all points. And in triaxial, what we do, we move this sample up. So when we move this sample up, when we make this sample go up, so on the top we have attached a proving ring. All right. So as this bottom part will go up, what will happen? The proving ring and the soil will interact with each other. The proving ring will push on the soil and the soil will push on the proving ring. And the soil will first compress the proving ring and the dial gauge will rotate. All right, so it will get compressed. So we will measure the compression, all right, of the proving ring. So from the proving ring constant and the compression of the proving ring, we will then measure what is the reaction, action and reaction between the proving ring and the sample of soil. And then ultimately at a particular point, what will happen? The soil will not be able to exert any more force onto the proving ring. So the force exerted by the proving ring will show a constant value. All right, and the sample of soil will go on shearing at that value. So just like this. So we go on pushing the soil up, 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 up. All right. So here the force is increasing. The force is increasing, increasing, increasing. At a particular value, the soil cannot push it anymore. That means it has reached its maximum point. So from there on, it will show a decline. So it will shear off. All right. It will start shearing. It will start failing. All right. So that is what we measure in the dry gel. So we have this soil. So we apply the cell pressure. The cell pressure is acted on the soil sample from all direction, and we have the deviatoric stress which causes the shearing. All right, so this is the deviatoric stress. So this is the principal plane. All right, this is the principal plane where this stress plus the stress from the fluid in the cell on this plane, that is sigma d from here. So this is sigma d, and sigma 3 from the fluid pressure plus sigma 3, we get the sigma 1 on this plane. All right, and similarly that sigma 1 will be transmitted, and since it is fixed at this portion, so we will have a sigma 1 from the bottom reaction as well. So these two are the principal planes, major principal planes where sigma 1 is acting, and these are the minor principal planes where sigma 3 is acting. All right, so we will come to that step by step. So here we see, so we have sigma 2 here, it is written, so we can say sigma 3, same thing. So sigma 3 is acting from the fluid pressure all throughout the sample, and here delta sigma or sigma d, whatever you say, so delta sigma or sigma d, whatever you say, so that is additional stress onto the plane normal here, normal plane here, or the horizontal plane here. All right, so that you kindly remember, because we are going to again come back to that at the end of the discussion. So yesterday we have discussed already that when there is an element and we apply a force, the force is transmitted through the element. So if we consider a plane on that element, so we have this plane, so this force is transmitted through this onto this plane here. All right, so we can consider the force P acting on this plane here. Similarly, on the opposite part here, so this P will be here, and on this plane, on the other side of the plane, there will be the opposite reaction of this force P. So at each and every plane of this element, we have a force P, which is acted on by one part of the element onto the other part. All right, so this we have discussed yesterday in detail. So once we obtain this P, we resolve this P into two. One is the normal force, and one is the tangential force. One is the tangential force. So if we divide the normal force F by A, so that is the normal stress. And if we divide the normal tangential force by the area on which it is acting on, all right, so this is area, then we have the shear stress. So this is the normal stress and this is the shear stress. Okay, so this is how it is represented. All right, so it is acting at all points of the plane. That is the stress. All right, so stress into the area is the force. Okay, so stress into the area is the force. So ultimately what we can do, so here you see, so this is theta, So this is F and this is P and this is theta. So this is cos of theta. Alright, so P cos of theta, that is F. And if we resolve it in this direction, so same thing here. So this is sine of theta. So P sine of theta, that is V. Alright, the tangential or shear force. Alright, so that is what we have found. And divided by A theta. Alright, so divided by A theta. So here what they have shown is, so they have divided by A theta. So if this is A theta, if this is A theta, then this plane A naught is equal to A theta cos of theta. We have discussed this yesterday as well. All right, so this is ultimately, so we can say A theta is equal to A naught by cos of theta. Okay, so A naught by cos of theta. So ultimately we have sigma theta is equal to this value and tau theta is equal to this value. So now again we come back to this rubber sample that we use to understand how the force is transmitted. All right, so what I will do is, so again we will come back to this rubber sample here. All right, so what the arrow is showing is, so the middle arrow is basically the force which I am applying. All right, so I am applying a compressive force in this manner. All right, I am applying a compressive force in this manner. So it is getting compressed. All right, and this is the blue color arrow is the reaction which I am getting from the rubber. All right, and if we consider a plane at the bottom, at any intersection here, so this part is exerting a force this onto the top part, and the top part is exerting this force onto the bottom part, or on any plane in fact. All right, this I am just taking one plane on any plane. So if this sample, if it shears, it will shear off like this in this manner. All right, so it will shear off in this manner. Okay, so the force is acting downward here and this force is acting upward. All right, and the forces on the plane I have already shown here. All right, of course we are going to discuss it in detail in the PPT again. So just remember that the sample will shear off in this manner like this. Okay, in this manner like this. So we have a shear plane there. Okay, so coming back to the figure here, so we have this force. So this is the force which I applied. This is the force which I applied. So this is a compressive force, and these are the reaction from the sample. All right. So if I could attach a proving ring here, I could have measured what is the force I am applying. So through the proving ring, I am applying this force, and what is the reaction the soil sample is applying on the proving ring. So I can measure the sigma d. Okay, and then we saw that the sample it failed along a shear plane. All right, so these are the forces which are acting on this wedge as we have discussed. All right, so this force it is transmitted to here on this wedge. This wedge is applying a reaction in this direction, and similarly it is applying a reaction in this upper towards the top, or in the upward direction, and similarly this part is applying a reaction in the downward direction, and this is the reaction it is giving to my finger, or in case if it is a proving ring, to the proving ring. Okay, so if I apply a pressure here, that will resist from shearing, this top part from shearing away. If this is removed, it will shear off. So the amount of force required to shear will depend on the normal stress which are being applied. So if we apply a more amount of confining stress, more amount of normal stress will be required to cause the failure. If we release it, less amount of normal stress less amount of this axial stress or deviatoric stress will cause the shearing of the sample. All right, now what we do, we will isolate this wedge, this triangular wedge. All right, we will isolate this triangular wedge. So if we consider this wedge here, so we have this force and this force acting on this wedge. All right, that can be resolved into two components, this and this. So this force can be resolved into two components, this and this. Now this force, it need not be resolved because it is already, this plane is normal. So this force is already acting, or this stress is already acting normal to this plane. So there is no shear stresses on this plane. So this is a principal plane. Of course, major or minor we will see it later. This is a principal plane. And similarly, we have the stresses here in the normal direction on this plane. All right, so that is a principal plane again. So we have this wedge here. Okay, and these are the stresses which are acting on the wedge. So if we consider this to be sigma 1, this is sigma 1 here, so this is sigma 1, this is sigma 1, and here if we consider the confining stress as in triaxial, so this is sigma 3, and obviously here we have the sigma n. All right, so so this is the sigma n, and this is the tau theta. All right, so just now we have seen what is the stress and what is the force. Now the thing is, so we have this wedge over here. So now what we have to do, to express sigma n or sigma theta and tau theta in terms of sigma 1 and sigma 3, we have to convert that into force first. All right, we cannot sum up the stresses because the area of actions are different. So this area is different, this area is different, and this area is different. So all the three areas are different. Therefore, we have to find out what are the forces which are acting in each direction. All right. So this is sigma n, sigma x, sigma y, and tau theta. So to do that, what we do is we rotate it such that this is the x-axis and this is the y-axis. All right, and then we resolve the forces in this direction. Okay. So here if we consider sigma n, so sigma theta, if I write sigma theta into suppose this is I consider as to be A, this area. Okay, sigma theta into A. So we have this force, sigma theta into A. So equal to, now this we require in this direction. All right, so this area, first of all, let us find out what is this area. So this area is, if this is theta, this area is a sine of theta. The area is a sine of theta. And what is this area? This area is a cos of theta. So the total force which is acting on this one is sigma 3 a sine of theta. Alright. So this is the total force. This total force sigma 3 a sine of theta. Now that we have to again resolve it in the x direction, in the direction of sigma theta or sigma n. So that will be sine of theta. Alright. So sigma 3 a sine theta. So this will be sigma 3 a sine theta into sine theta. Alright, or we can say a sine square theta. Alright, or we can say a sine square theta. So similarly we have a cos of theta. So this is the force. So if this is theta, alright, so this is sigma 1 a cos theta is the force, and this is the component of the force in this direction, x direction. So that will be sigma 1 a cos of theta into cos of theta, or we can say sigma 1 a cos square theta. Okay. So similarly, you have to find out the components in the y direction. Alright, so here in the y direction, tau theta is equal to tau theta into a is the force, and similarly you have to find out what is the component in the y direction. Okay, and then you have to add it. So ultimately you have to add summation of forces in the x direction. Alright, so all forces in this direction or this direction you have to add, and similarly all the forces in this direction or this direction you have to add in this. Okay, so you will find out the expression for sigma theta and tau theta in terms of sigma 1 and sigma 3. And if, alright, so ultimately we have this particular expression. So we have this sigma 3 here, and this is sigma 1. Alright, and then we have, if this is theta, so we have sigma theta is equal to sigma 1 plus sigma 3 by 2 and sigma 1 minus sigma 3 by 2 cos of y theta. Alright, so we have to find out, you have to convert it into forces. And if, now here these are all major principal planes. This is the major principal plane and this is the minor principal plane. Alright, these are all principal planes. So why principal planes? Because there are no shear stresses. Okay, there are no shear stresses. If there is a shear stress on the plane of where it is applied, so ultimately you will have a component from the shear stress, alright, on the plane of concern and as well as here. So in case of, if these two planes are principal planes, then this term will not appear. Alright, and we have this expression here. Okay, and we have this expression. So the thing is that you find out, so here we have rotated, so this in this direction you find out all the components of this force and of this force. So all the components in this direction and this direction. So this is the x direction. Similarly, when we consider the tau theta, so tau theta is in the y direction, all right? So all the components in the y direction, all the components in the y direction, all right? So you add it up, all right? All the components in the y direction, and you add it up, and ultimately you will arrive at this particular solution. Now this we have to remember, because while observing the stress path, we will see how this is important. Okay, we will see. So we have this expression over here. So in case of triaxial, since we are applying only sigma 3 and sigma 1, so this is the major principal plane, and this is the minor principal plane. Sigma 1, remember, is always sigma d plus sigma 3. Okay, so sigma 1 is always sigma d plus sigma 3. Sigma d is applied through the proving ring, through the ram, and sigma 3 is the cell pressure which is being applied all around. All right, whatever we have discussed. So now, if you plot this function, for various angles of theta, so if I take theta 0, 1, 2, 3, 4, 5, so what I will get is, I will get a circle. All right, so the equation is sigma 1 plus sigma 3 by 2 plus sigma 1 minus sigma 3 by 2 cos of twice theta. So if I change the values of theta from 0, 1, 2, so what I will get is, so I will get sigma theta values at various thetas. So similarly, I will also get tau theta values. So tau theta is equal to sigma 1 minus sigma 3 by 2 sine of twice of theta. Alright, so here if I plot sigma, suppose I take theta is equal to 0, tau theta is equal to, tau theta is here also is 0, so theta is equal to 0 in both the case, and I plot. So tau theta is equal to will be 0 because sine of 0 is 0. Alright, so where will tau plot? Sigma 1 minus sigma 3 by 2. Okay, so it will plot here. So here, sorry, 0, 0, it will be theta, so sorry, it will be 0. So this will be 0. So tau theta, if when 0, theta is equal to 0, so tau theta is equal to 0. So it will plot here. Okay, then I increase to 1, theta is equal to 1 degree. So theta is equal to 1 degree, 1 degree. So I will get a value of tau theta and sigma theta. So I will plot it here. It will plot here. Then I increase to 2, theta is equal to 2, and so I will get a value of tau theta and sigma theta and tau theta. So I will plot it. So I will get the value here. So ultimately, if we plot these two coordinates, we will see that it plots a circle. It plots as a circle. So 0 to 180 degree to 360 degree again. Okay. So what does it signify? So what does this Mohr circle signify? So it signifies the normal stresses and the shear stresses at the planes of various angles. All right, at the various angles. So that is what the Mohr circle signifies. Okay, so when we say stress state at a point, so at a point there are numerous planes which are passing through the point. So numerous planes which are passing through the point. So all these planes will have different orientation. So what is the stress state? So this Mohr circle gives a comprehensive view or comprehensive idea about the stress state at that particular element. All right, so when we have sigma 3 and sigma 1 applying in an element, so at various planes, what is the stress condition? So if theta is the inclination of the plane as it is shown here, so as it is shown here, so theta is the inclination of the plane here. So this is the inclination of the plane. Okay, so this is the inclination of the plane. Theta, it is given 53 degree. So twice of theta is 106 degree. So here, from here you plot twice of theta, and this is the stress condition here. So this is the shear stress, tau. This is the shear stress. Value of shear stress, that is, this is the shear stress value acting on here, and this is the value of the normal stress acting on this plane, on this plane, that is. If we consider this plane, then we have to increase the angle of inclination up to this one. So here what we have is, this is the shear stress and this is the normal stress. This is the shear stress, this is the normal stress. And when we consider a plane, so theta is equal to 0. So we have, theta is equal to, 0. All right, or theta is equal to 90 degree. All right, so when it is theta is equal to 90 degree or 0. All right, so in case of 0, it will be here. All right, so that is sigma 3. All right, so that is the sigma 3. And in case of 90 degree, so this plane, so 90 into 2, so we have 180 degree. So this is the sigma 1 here. Okay, and this is the deviatoric stress, sigma d. So sigma d is equal to sigma 1 minus sigma 3. So we have been discussing that sigma 3 plus sigma d is equal to sigma 1. So that is the load which we are applying in a triaxial case. In a triaxial case, that is the load which we are applying. So that is the sigma d. All right, so we have been applying that. So in this case, so we can say sigma d is equal to, so if I take sigma d, yes, so sigma 3 will be there in this side, so it will change the sign, sigma 3, sigma 1 minus sigma 3. So that is the diameter of this Mohr circle. All right, so you remember this point. Okay, this point is very important because this point will follow how the Mohr circle will go on increasing with increasing load. All right, if you understand this equation, in fact, I think you have understood. If you have understood this equation, that means you have understood how the Mohr circle will go. So this is sigma d. Okay, this diameter of the Mohr circle.
Sir.
Yes.
Sir, একটা question আছে স্যার।
Yes, yes.
স্যার, যদি আমার মানে এটু যদি প্রিন্সিপাল প্লেন হয়, যত সিগমা 1 অ্যাক্ট কৰি আছে, মানে যদি আমার শিয়ারিং স্ট্রেস থাকে, তেনেহলে তো প্রিন্সিপাল প্লেন চেঞ্জ হৈ যাব স্যার।
Then how
যোনটো প্লেনত শিয়ারিং,
then
হেতু মানে
how to plot that? If there is a tau, yeah.
স্যার, প্লটিং মানে একচুয়ালি তেতিয়া যোনটো মেজৰ প্ৰিন্সিপাল এক্সিস হ'ব। এসাইনমেন্টত এটা কোশ্চেন আছে, মেজৰ প্ৰিন্সিপাল এক্সিস তেতিয়া কোনটো মানে হৰাইজন্টাল বা হৰাইজন্টালৰ লগত আৰু ভাৰ্টিকেলৰ লগত কেনেকে এংগেলটো কৰিব।
So in that case, this will be sigma y and this will be sigma x. Okay, and this will be tau. Yes,
মানে স্যার এটু স্যার, yes sir,
yes,
এটু মানে স্যার
so
graphically,
graphically I am telling you graphically only, understand that graphically.
স্যার অলপ মানে হেৰি লাগিছিল, মানে এনালিটিক্যাল লাগিছিল স্যার, এনালিটিক্যালি
Yeah,
এঙ্গেলটো বুজি নাপাওঁ স্যাৰ
this is the analytical. This is the equation.
কিন্তু স্যাৰ এঙ্গেলটো কোনটো মানে এঙ্গেলটো থিটা এইটো এঙ্গেলটো থিটাই হ'ব
No, this is the element. So you are applying sigma x and sigma y and tau x. Yes, and
Yes, sir.
this is the angle of inclination with this sigma x theta. This is the angle of
Yes, sir.
inclination in this case.
Yes, yes, sir.
And if you want to find out the angle of inclination of the principal plane, then there is also an expression being derived. I have already discussed that, and I have given that in the material also. So you can also find out what is the angle of inclination of the major and minor principal plane corresponding to this direction. Corresponding to this direction. Okay, so if you are given a question or a problem where sigma y and sigma x is given, and you have to find out what is the theta, stresses on a plane which is inclined at an angle theta, then this is how it is done. Okay, so this is how it is done. So ultimately, again, you take the triangular wedge. So here in this case, this will be sigma n, this will be sigma tau theta. All right, and here in this case, so there will be sigma y and this will be tau xy. And here in this case, it will be sigma x and here it will be tau xy or yx. All right, so in this case, it will be yx, so this will be yx and this will be xy. All right, just as in this case. So ultimately, you find out what is the force equilibrium. What is the force equilibrium? So if this is the condition, similarly as I have discussed in the previous case, so you take this sigma as is shown. So this is sigma n. This is what, or sigma theta, this is what we require. Okay, and this is tau theta. This is what we require. This is what we require. So we have sigma x, or this is sigma y. All right, and this is tau x, yx, tau yx, and this is sigma x and this is tau x y. All right, so first you consider this force. So this force, you resolve it into two components. This force you resolve into two components, this two components. Again, similarly, this shear force will be resolved into two components. Again, shear force will be resolved into two components. All right, so this force will add up, this force will add up, this force will add up. All right, all the horizontal forces will add up, and all the vertical forces will add up, and ultimately the vertical forces will lead to this expression here, and the horizontal forces will lead to this expression here. All right.
Yes, sir. Yes, yes, sir.
Yeah. So thing is that you are getting. You are actually panicking. It is not like that. You solve one condition at a time. Just like here, what I have done is, I have rotated that. All right. So here, I have rotated the thing. All right. So this is the normal stress into the area. So force, I have to convert this into force. So normal stress into area, that is the force. Again here, normal, this tangential stress or shear stress into the area. So this is in the y direction, this is in the y direction, and this is in the x direction. So similarly, this sigma 3, you have to find out the area here. So here there will be another shear force or shear stress. So as we have resolved this stress component or this force component into two components here, similarly this also we will resolve it into two components. Okay, first thing that you do is you find out the area. So area, if this is area A and this is area A naught A sine theta and this is area A cos theta, if this is theta, so that is the area. Then you multiply all the stresses which are acting on that into the area. So that will give you the force in that direction, in the direction of the stress. Remember that. Alright, so here if I multiply sigma 3 into A sine of theta, so this will give me the force in this direction. So this force is directed in this manner. So I have to resolve it into two components. So then only this will add up to this, and this component will add up to this one, y-axis. So this is in the y direction, this is in the x direction. Similarly, also the shear force stress which is acting. So if this is tau x y or tau, suppose tau only, all right. So tau into A sine of theta is the shear force, is the shear force on this plane. So this plane, it is acting in this direction, this force. So this force, it is acting in this direction. So what we have to do, we have to resolve it into two components, one in the x direction and one in the y direction. So the x direction will add up in this equation. All right, so summation of fx, and the y component will add up in the summation of y. Okay, and ultimately you will come up to this equation. All right, so that is the thing. So do not panic.
Yes,
And
yes,
here also, graphically also, you can find out if you know sigma y, sigma
yes,
x and tau. So what you do, you plot tau, so this is tau, and you plot sigma x, so this is sigma x, and this will be sigma y, so this will be sigma y and this will be sigma x, or maybe opposite. All right, and you draw this. So this is the diameter, so this is the deviatoric stress, and ultimately if you complete, so you get the center. All right, if you complete the circle, you will get the major principal plane also. So this is the graphical method. All right, so ultimately everything is within this Mohr circle. All state of stresses, whether there is shear stresses or not, principal in the principal planes, there are no shear stresses. Whenever there is slight, change in the angle, so there is shear stresses being developed. So as it will go on rotating, so we have shear stresses acting on the planes. All right, so that is how you do that. And this is the two-dimensional and three-dimensional. So here you see these are all the normal stresses. So these are the normal stresses on the planes, and these are the normal stresses on the planes. All right, and these are the shear stresses. And one thing you remember, for rotational equilibrium, tau yx should always be equal to tau xy, or else this element will start rotating. All right, it will start rotating. So for rotational equilibrium, so this is condition has to be fulfilled. Of course, that we will discuss later on. So today I will quickly complete this. So we have this three-dimensional. So we have this sigma x, sigma y, and sigma z. So sigma x, sigma y, and sigma z. All right, and then you can see tau xy, tau xy, tau yz, tau yz. Right, and similarly the other three components. So this is a three-dimensional stress tensor. All right. So in triaxial, the advantage is that we are already in the major principal orientation. So we have sigma 1, which is the major principal plane, and we have sigma 3, which is the minor principal plane. So we already are in the principal plane orientation. So we just plot sigma 1 and sigma 3. Okay, and we get the Mohr circle. So this is the Mohr circle that we get. Okay, so this is the failure plane if it touches the failure surface. If it touches the failure surface, this is the failure plane. Okay, so as we have discussed, I think it is already time. Okay, tomorrow, yeah, tomorrow I can have the class. Okay, okay, tomorrow we will have the class. So this we will continue tomorrow. Okay. So this part, okay, tomorrow I will just, give you the derivation of this, when there is this one, okay? I will just show you the derivation. Then it will be, at least the forces, what are the forces which are acting, I will list you out. So then it will be okay, because anyway,